In a world inundated with information, how do we sift through the noise to find the nuggets of wisdom that truly matter? Hello, I'm Richard Walker, founder of Lucidate, where we harness the power of artificial intelligence to illuminate the complex landscapes of capital markets. It's increasingly common to use AI for text summarization, machine translation, or code generation. But how can we evaluate which AI model is best suited to which task? That is the subject of this video. For our AI systems, we have a bewildering array of choices of large language models to choose from foundation models hosted in the cloud, specialist models from Hugging Face, models we've fine-tuned ourselves, models running locally on our own machine. How can we objectively determine which model is best for any given task? Put another way, as we delegate the task of understanding and summarizing this world of words to machines, a pressing question emerges. How do we measure the accuracy and integrity of these machine-generated summaries or translations? How can we tell which LLM is best suited for a particular summarization task? In this video, we'll discuss 3 metrics for evaluating how well individual LLMs perform on specific summarization tasks. These metrics are called BLEU, ROUGE, and Semantic Similarity. We'll show an application that can compare different LLMs and generate a league table that ranks each model from best to worst. Stick around until the end of the video to find out how, by subscribing to Lucidate's channel, you can get access to the source code to rank these models so that you can run your own benchmarks on your own machine. So let's meet BLEU and ROUGE, the dynamic duo of evaluation metrics tasked with a critical mission to measure the effectiveness of machine-generated summaries. But what makes these metrics the gold standard in the realm of NLP? BLEU, or the bilingual evaluation understudy, shines a light on precision. It's like a linguistic detective analyzing how closely a machine's output matches with our human benchmarks, piece by piece, word by word. While BLEU focuses on precision, ROUGE, the recall-oriented understudy for gisting evaluation, predominantly prioritizes recall. It ensures that the machine summary doesn't miss out on any vital information, capturing the essence of the original benchmark text. At the heart of both BLEU and ROUGE lies the concept of n-grams, sequences of n words used to capture context and meaning, from unigrams, which are single words, to bigrams, trigrams, and beyond. N-grams help us evaluate the linguistic quality of machine summaries, ensuring they're not just accurate, but meaningful. To see how n-grams work in action, let's look at the phrase, "The quick brown fox jumps over the lazy dog." We'll see how n-grams are used to quantify how closely similar phrases match this one. With both BLEU and ROUGE, we can quantitatively assess the similarity, identifying overlaps and ensuring the machine's rendition holds true to the original's intent and information. So, how are they calculated? Well, look, let's start with an analysis of n-grams, the building blocks of our linguistic analysis. In this scenario, we're focusing on bigrams, pairs of consecutive words that help us grasp the sequence's context and flow. As we highlight each n-gram in any machine-generated summary, we're preparing to match them against our golden source, the human benchmark for accuracy and completeness. Now, observe the golden standard. Our goal, well, in this specific case, to identify how many bigrams from the machine's attempt find their place in this golden source. We're additionally performing this process for unigrams, trigrams, and all the other n-grams in our analysis. Each match lights up, symbolizing a bridge between the machine output and the human excellence. The non-matches, well, they remind us there's always room for improvement. For each Y that appears, a match is confirmed. The N's, well, they're a miss. And here unfolds the magic of BLEU, a simple yet powerful calculation. We tally up the matches, the Ys, and set them over the total number of bigrams we examined. This ratio, well, it's a glimpse into how well our machine's language aligns with our human touch. In our case, for these bigrams, we have a score of 0.5. This tells us that for every 2 bigrams in our machine summary, one finds its counterpart in our golden source. This is BLEU in action, quantifying precision, guiding machines to mimic the intricacy of human language. But that's just for the bigrams. We need to take into account all of the other n-grams in our analysis too, to arrive at the final calculated BLEU score. So to calculate the BLEU score, we use the formula on your screen. We look at the ratio of unigrams, bigrams, trigrams, etc. that match in the machine-generated and golden source record. As we increase n, the number of consecutive words in our n-gram, it becomes harder to generate matches and our score plateaus. This BP, this brevity penalty, is there to ensure that our generated summaries are not only accurate, but also complete. For a very short summary of only a few words, it might be possible to match every n-gram and game the index. Our BP variable ensures that this is not the case. As we delve into the ROUGE metrics, it's important to understand that ROUGE is not a single score, but a family of scores, each tailored for specific evaluation needs in natural language processing tasks. Let's explore these metrics and their ideal use cases. First, we have ROUGE N, which focuses on the overlap of n-grams between the generated summaries and a set of reference summaries, the golden source. This metric measures both precision and recall, providing a balanced view of summary quality. While precision focuses on the exactness of the generated summary, recall assesses its completeness, i.e. what's missing. In tasks where capturing all critical information from the original text is paramount, a high recall score is particularly valuable. Next, we encounter ROUGE L, which values the longest common subsequence between summaries. This metric leans towards evaluating the fluency and readability, making it ideal for summaries where the flow of ideas is crucial. Following ROUGE L, ROUGE W introduces a weighting scheme to prioritize longer contiguous sequences of matching words, aiming to maintain the logical flow of complex texts. Lastly, ROUGE S allows for more flexibility by measuring skip bigram co-occurrence statistics. Quite a mouthful. This metric shines in scenarios where capturing the essence and key points creatively is more significant than exact n-gram matches. In summary, the ROUGE family of metrics offers a comprehensive toolkit for evaluating the quality of machine-generated summaries. By understanding and utilizing these metrics appropriately, we can ensure that our models not only replicate the facts accurately, but also preserve the essence and coherence of the original texts. Now, let's shift our focus to a concept equally vital, if not more so, in evaluating machine-generated text, that of semantic similarity. Unlike the n-gram-based metrics, which match sequences of words, semantic similarity delves into the meanings behind words, capturing the essence of text beyond surface-level matches. Semantic similarity measures how closely the ideas or concepts in the machine-generated text align with those in the reference or golden text. This involves understanding synonyms, context, and the nuanced relationships between words. For instance, while fast and quick are not identical words, they share a similar meaning, and semantic similarity metrics will recognize this alignment. One common approach to calculating semantic similarity involves vectorizing the text, where words, sentences, or entire documents are converted into numerical vectors based on their semantic properties. Techniques like word embeddings, where words with similar meanings are mapped to proximate points in a high-dimensional space, play a crucial role here. By comparing the vectors of the machine-generated summary and the reference text, we can compute a semantic similarity score. A higher score indicates that the two texts share a similar meaning, even if they use wildly different words or phrasings. Correspondingly, lower scores indicate that there is little overlap in meaning between the machine-generated text and the target. On your screen, you can see the scores generated in 3 dimensions. Word embedding vectors are typically in the thousands of dimensions. If you can figure out how to render a 1500 dimensional space on a YouTube video, please leave a summary in the comments. The significance of semantic similarity in evaluating summaries cannot be overstated. It allows us to capture the true intent and meaning behind the words, offering a more nuanced assessment of a summary's accuracy and coherence. In essence, it ensures that our machine-generated summaries don't just repeat the words, but truly understand and convey the original message. So with these foundational concepts in hand, we're now ready to see them in action. Join us as we demo an application designed to measure the accuracy of machine-generated summaries using BLEU, ROUGE, and semantic similarity scores. Witness firsthand how these metrics come together to guide and improve the quality of automated summarization. Now, there are plenty of pre-existing implementations of things like BLEU, ROUGE, and semantic search. You can use the NLTK, or Natural Language Toolkit, as well as some routines from scikit-learn. So you don't have to worry about coding your own models. As you can see with this class on your screen, it's simple to create your own classes to calculate these metrics, given your LLM-generated text and any given reference benchmark. Let's take a look at the benchmarking application in action. We want to determine which language model provides the best summarization capabilities. To do this, we'll need a reference text and a reference summary, our golden source. While the summary would naturally be subjective, this is the optimum gold standard summary agreed on by experts at your firm. This is the target that the LLM is being measured against. Using BLEU, ROUGE, and semantic similarity, we're quantifying the ability of any given LLM to get as close to the summary as possible. We measure this both in terms of n-gram matching for BLEU and ROUGE, as well as the overall closeness in meaning using semantic similarity. For this benchmarking process to be accurate in your firm, it's crucial that you continually challenge yourselves to ensure that the target golden summary is the very best summary for your purposes, and change it if you feel that a better summary exists. So, with all that said, let's take a closer look at the application. Here's the source article we're using for our benchmark, and here is our golden source summary. As I said, you should never be afraid to tweak the summary to make sure it truly reflects the best possible human summary that your firm could come up with for your own summarization use cases. There are a couple of drop sites on the left of the app that you'll use to drop your article and golden source summary into. You can then choose which large language models to compare. In this list, I have a mix of hosted models such as OpenAI's GPT, Anthropic's Claude 3, a local model, Llama 7B, running on my own machine using Ollama, Coral from Cohere, and finally, a fine-tuned model, Lucidate, which is a model I've fine-tuned with macroeconomic information to make it suitable for asset management tasks. When we run the application, we can first see the golden source displayed on the screen. This is our target summarization that our LLMs are seeking to accurately emulate. As each LLM summarizes the source text, a container appears in the user interface that we can inspect to see that particular LLM's specific summarization. We can take a look at the summarization from GPT-3 by clicking on the container. Similarly for GPT-4. If you want to pause the video at the appropriate points, you should be able to see the summarization that each model provides. Even the 7 billion parameter Llama model running on my own machine does a very creditable task of summarization. After Cohere's Coral, we then see the summary generated by the Lucidate fine-tuned model. With all of these summaries generated, we can then display the BLEU, ROUGE, and semantic similarity scores. Here I've used three different visualizations for the same data. The first is a grouped bar chart. The LLMs are color-coded and the grouping is by metric, with BLEU on the left, the various ROUGE metrics in the middle, and semantic similarity on the right. This is followed by a table of metrics, with the gold color coding being awarded to the leading LLM for each metric. In this case, you can see that the Lucidate fine-tune model scored highest in each category, which you can also see clearly in the radar plot below. Now, this is not to say that the Lucidate fine-tune model is the best model, merely that with the given hyperparameters, this particular fine-tune model performed best for this particular task. Given that this model was fine-tuned with economic data suitable for an asset manager, it perhaps shouldn't be a surprise that this fine-tuned model was the category leader. Were this task to summarize a non-financial text, then one might not expect this model to be so dominant. Now let's put it another way. If the Lucidate fine-tuned model did not smash the others at this task, then what's the point of fine-tuning? And to drive this point home further, if you do produce a fine-tuned model, how can you tell it was worth the additional effort? Unless you adopt a rigorous testing approach, such as the one illustrated in this video, you won't be able to demonstrate to yourself or other stakeholders that the fine-tuned model is any better than the foundation model it was trained on. When you experiment, make sure to clinically and dispassionately evaluate your results, as true in AI as in any other discipline. In the next video, we're going to look at a superficially similar but technically very, very different challenge. Rather than looking at text summarization, we'll be looking at code generation. For this, we'll need an entirely different set of metrics from BLEU, ROUGE, and Semantic Similarity to evaluate code gen. We'll explain these different metrics in that video and see them in action using some LLMs specifically designed for code generation rather than NLP. Finally, I mentioned at the beginning that the access to code for these benchmarks was available to Lucidate subscribers. This code will be available to any Lucidate YouTube subscriber who leaves their GitHub ID as a single word in the comments section. You'll need to either be subscribed already or subscribe on this video. To trigger this, you'll need to leave just your GitHub ID, no punctuation and no other text in a single comment. This way, the comments can function as comments for those who wish to leave a comment. If you just leave your GitHub ID, you'll be automatically added to the repo. Any other text and you won't. So if you type, "Hey, Lucidate, great video. I'd love access to the GitHub repo. My GitHub ID is RTFM." You won't, I repeat, won't get access to the repo. Only one single word in a single comment. Then wait 24 hours after you've left your ID as a single word in the comments, and you'll get an email from GitHub with instructions on how to join the repo. This is Richard Walker from Lucidate signing off. Stay tuned for the next installment on validating code generation models.